little question. Okay, so we're going to look at forces between wires. So if we have two wires carrying currents, they're going to exert forces on each other. So let's look at, say we have wire 1, which say has a current I1, and let's just say we have two parallel wires. And say the currents are in the same direction, just in this example. And these wires are going to exert forces on each other. Now the question is, why do they do that? And well, let's look over on the right here. Now remember, currents create magnetic fields. So let's start at the bottom here. Let's say we have a wire coming out of the board. Remember, magnetic field lines, if you have a long straight wire, the magnetic field lines curl around the wire, and the direction is given by the right-hand rule. So here are the currents coming out of the board, magnetic field lines curl around this way. If the wire is going into the board, they would curl around this way. And so, in one sense, a wire creates a magnetic field around it. So let's say I2 is there's a magnetic field due to wire 2. Just in the space around wire 2, there's a magnetic field. And magnetic fields exert forces on currents. And so, if you look at current 1 is existing in a magnetic field created by wire 2. And so the magnetic field of wire 2 is going to exert a force on wire 1. Similarly, wire 1 is creating a magnetic field in the region of wire 2. And so there's going to be a force on wire 2 due to the magnetic field of wire 1. So there's kind of, in a sense, nothing new. Theoretically, I could just give you this problem and say, figure it out. What's the force between them? But there's kind of a lot of steps involved. And it's a little tricky. You have to be very careful about directions. So it kind of deserves its own topic to just go over a problem like this. Now, fortunately, Newton's third law applies in this situation. So we only have to look at one of these cases. Let's find the force on wire 1. Now, very important, I'm going to delete wire 2 for a moment. Now, wire 1 creates a magnetic field around it. Does that field exert a force on the wire? No, we're treating the wire as just an object. Things cannot exert forces on themselves. So if we want to know the force on wire 1, this force on wire 1 exists because of the magnetic field of wire 2. So we'll use this top equation. We'll say that each wire has a length L. Okay, so we want to find the force on wire 1. So let's just start writing it down. This would be the current due to the current carried by wire 1 times the length of the wire. We could give them different lengths, but let's not do that. And then we have B2. The force on wire 1 is due to the magnetic field of wire 2. So we'll call that B2, and we'll put, sine of theta in here. So we have to figure out what that angle is. And again, this is just the magnitude of the force. We also want to know the direction of the force. So we need to know what B2 is, the magnetic field due to wire 2. So in this case, we look at wire 2, magnetic field lines circle around, and again, so you put your thumb in the direction of the wire, and fingers curl around this way. So here, the magnetic field lines of wire 2 loop around like this. They come out of the board here, then they go into the board, loop around, and come back out. We only only care about what it looks like over here, and so we can see that they're coming out of the board. So, yeah, again, they're coming out of the board here. Now, if wire 1 was down here, then the magnetic force would be into the board and the direction could be different. But here they are coming out of the board. And so, remember the theta in this formula is the direction between the wire and the magnetic field, and we can see they're perpendicular to each other. So, that's 90 degrees. And sine of 90 is 1. So we can ignore this moving forward. Now from Ampere's law, we found the magnitude of the magnetic force a distance r from the wire. So, yeah, the field gets weaker the farther away you are from the wire. And yeah, just very easy calculation using Ampere's law. So B2, let's plug that in. So we have I1 now B2, this would be mu naught I2 divided by 2 pi, let's just call that R. We'll say the distance between the two wires is R. Also, we'll make an actual problem out of this. Let's say I1 is 3 amps, I2 is 4 amps. Let's say L is 1 meter. Let's say R is 9 centimeters. All right, just so we have numbers to work with. But before we do that, let's kind of clean this up a little bit. Let's put the mu naught in front. Okay. So that means the force on wire 1. I think we've got everything here. Now this is the magnitude of the force on wire 1, but look at how these currents show up. It doesn't matter if you switch the wires. They show up the exact same way. Again, this is just Newton's third law. The force on wire 2 is going to be the exact same magnitude. So we can just call that F in general, the force between these two wires. Okay, now we also want to know the direction of the force. So let's look at this current going to the right. Remember, just in general from the right-hand rule, we consider like a conventional current. Say this current is composed of positive charges moving to the right. So again, you put your fingers in the direction of the velocity and curl towards the magnetic field. And so the force, because we're dealing with positive charges moving to the right, we have to curl our fingers this way for the magnetic field. So the force on wire 1 is going to be downwards towards wire 2. Now we could just stop there because we know Newton's third law applies. So we can say the force on wire 2 is upwards towards wire 1 just from Newton's third law. They have to be opposite in direction, but just practice for the right-hand rule. Let's actually find the force on wire 2 using the right-hand rule. So first off, the second form of the right-hand rule, the magnetic field due to wire 1 is going to be into the board over here. Let me do this. Should have probably done this from the beginning. So I use red for wire 2. So these red dots, that's the magnetic field due to wire 2. And then I'll use blue for wire 1. Okay, so for wire 1, at the location of wire 2, you can see the magnetic field lines are going into the board. And so using the second right-hand rule, consider a conventional current. You put your fingers in the direction of the current and curl towards the magnetic field. Thumb points in the direction of the force. So this would be F2. And we can see that that is consistent with Newton's third law. So these wires are attracted to each other. Now, again, it's kind of, just putting together a bunch of concepts that we've learned about already. But again, there's a lot that actually goes on in just finding the force between two wires. We have to use both right-hand rules. We have to use the second right-hand rule to find the direction of the magnetic field, and then the first right-hand rule to find the direction of the force. And use Ampere's law to find the magnitude of the magnetic field. And then use this equation to find the force on the wire. So again, it's kind of a deceptive problem. If I just said there's two currents, if I just gave you this information, there's a lot of steps involved in actually figuring out the force between the wires. So that's why it's good to just go over this as a separate topic. Okay. So in this case, the wires are attracted to each other. One more thing, we have two ways of writing mu naught. What I'm going to do is I'm going to write mu naught as 4 pi times 10 to the minus 7. And Tesla meters per amp. The other way is 1.26 times 10 to the minus 6. This is exact. Just mu naught is defined this way, so that is actually exact. What I'm going to do is I'm going to write the force between these wires mu naught over 2 pi. I'm just going to break it up into two pieces. So again, it's algebraically exactly the same thing. But mu naught over 2 pi, if we divide this by 2 pi, we just have 2 times 10 to the minus 7. So we have 2 Tesla times meters over 10 to the 7th amps. Now I1 times I2, that's going to be 12 amps squared. R is 9 centimeters. Here, let's just do it this way. L is 1 meter. I do it this way. 1 meter, I'm going to write that as 100 centimeters. And then R is 9 centimeters. Just because getting the force in the unit part is going to be the most difficult. As far as plugging it in, just getting newtons out of this. So let's just double check. We've got mu naught over 2 pi. That looks good. I1, I2, that's 12 amps squared. And then L over R. Those units are going to cancel out. Okay. So now let's see what unit conversion factors we need here. Now, one of them we might need is a Newton times a second is a Coulomb times a meter times a Tesla. So let's throw that in here. Newton times a second is a Coulomb, meter times a Tesla. Remember, an amp is a Coulomb per second. So if we multiply by a second, an amp times a second is equal to a Coulomb. So let's see unit-wise what we're going to get here. So let's just go across the top. I'll just do that here in this space. Okay, so we have Tesla, meters, amps squared, centimeters, newtons, seconds, and coulombs. And we're hoping everything cancels out except for the newton. So going across the bottom, here's an amp, centimeter, coulomb, meter, and Tesla. So amp, centimeters, coulomb, meters, Tesla, and then an amp and a second. Sorry. So the only thing we have left, so this actually does give us newtons. Everything else canceled out. Okay. So numerically, we have 24 divided by 9. So that's 2 times 12 over 9. And then we have times 10 to the minus 5th newtons. 24 over 9, that's around 2.7. So times 10 to the minus 5th newtons. So this would be like in micronewtons, basically. But, yeah, let's do that. I don't have room to write this down exactly, but I'll cram it in here. Yeah, this is about 2.7 times 10 to the minus 6 newtons. We can just leave it in, or 10 to the minus 5th newtons. Let's just leave that in scientific notation. So that would be the force. It's a very small force. But, yeah. That's, yeah, so kind of a deceptive problem because it's looks, if you just read the problem, looks like it's very straightforward, but there are a lot of steps involved in just getting both the magnitude and the direction. So in this case, these wires are attracted to each other. Okay, so kind of a short one, but really it's just looking at one particular problem. So that'll be it for this one.